Okay, so let's continue our discussion. So we saw the two different types of energy sources in the last classes, right? So like carbon dioxide, directly from the carbon dioxide, so CO2 fixers, as we call them, and you can take those organisms that don't do the CO2 thing, but they rely on organic molecules like sugar, right? So autotrophs and heterotrophs, right? So those who can directly take the CO2, they are autotroph, the others are heterotrophs, okay? We also have those that use light, phototrophs, and those that use the chemical energy, right? So the chemo heterotrophs and the chemo autotrophs, those kinds of things. Now, we saw electron transport chain. Today, what we will look into is very similar to what we do, and we studied that in geochem. So this concept of redox potential. We will not go in great detail, but just to remind you, we saw the standard reduction potential. Standard reduction potential. What was this? Do you remember? The E naught, also called the SRP, the standard reduction potential, in which you had the table of and so on and so forth. So, or maybe for simplicity, you started out with lithium, somewhere in the middle you had the hydrogen, or this is the platinum, the reference electrodes, and on this side you started to have all the non-metals and things like that. So we called them a table. What was this table called? Or what is the standard reduction potential? So with this, you would have a voltage associated with this, and this would have a negative, and this would have a 0 voltage, and this would have a positive voltage. The E naught, the standard reduction potential. So what was the standard reduction potential? The potential to be reduced, right? So like this was the potential to be reduced. Potential to be reduced. Not to reduce someone else, to be reduced themselves. So, if something has a negative reduction potential, that means it does not want to be reduced. It wants to get oxidized. Okay, that's why it has a negative reduction potential. On the other hand, the sulfate, has a huge positive standard reduction potential. That means it has a huge potential to be reduced, to get reduced itself, and in the process it will oxidize the others. So these end up being tell me, good oxidizers or good reducers? The lithium? It has a negative reduction potential. This wants to be oxidized itself. So this will do what to the others? Reducing agent. So this is a good reducing agent. Good reducing agent. Correct? So if it is a good reducing agent, will this be an electron acceptor or electron donor? It's a reducing agent. It is reducing someone else. So is it pushing is it an electron donor or acceptor? It's a donor. So these are the best electron donors. On the opposite, these will be electron acceptors, right? So based on this, I will not get into this because in geochem we have done it. This was the fundamental standard reduction potential and so on. With this, so in the standard electrode potential business, we typically tend to write the half cell reactions. What I mean by this is this. So when I'm writing these like reactions along with it, so this is a reaction and this is a half reaction, half cell reaction. Why do we call it a half cell reaction? Because in here, I am only trying to understand the reduction So we are only considering half of the reaction. And we only typically consider a reduction reaction. So even though the standard reduction potential is negative, I mean it is a much better, it has a much higher oxidation potential. We will always write the half cell as a reduction reaction because that's what we are writing. It's always represented as a reduction reaction. Okay, so any reaction that is written for the SRPs will be a reduction reaction. All these half cell reactions will be reduction. It's called half cell because we are only writing half of the reaction. Because can you have a reaction that is only reduction or oxidation? You cannot. Because you cannot have free electrons floating. So there is a counter reaction to this. In this case, there should be a source of this electron. Right? We are not talking about the source of the electron yet. In this reaction. So this is a mathematical way of representation. In actual nature, you will never have a half cell reaction. But in electrochemistry, what we do is very smartly, we have a reduction half and we have an oxidation half. And then we attach these things. Okay? And that is why we are only talking about the half cell reaction. And this half cell reaction is always with respect to the standard hydrogen electrode, which is called the SHE. Okay, so this is the standard hydrogen electrode. So just remember that there are all these highly reducing, there are these electron donors with very negative electron, the standard electrode potentials. And we are writing, so this will have an E naught something -4 or there's some voltage associated with it, I don't remember. But these are calculated with respect to this. So potential is always calculated with respect to a standard. So this standard happens to be this. Okay. For example, the potential, the gravitational potential. So you always have a potential which is like the base, and you always calculate the potential, the mgh, with respect to that potential. So if the ground is 0, then the potential of this thing will be positive, anything below it will be negative. But someone can also say, hey, I will not assume this as the 0 potential state. I will assume the basement, the flan, this is 3, right? So I will consider flan 2, the second floor of this as the, someone will say, hey, no, I will consider the first floor. So they can choose any baseline, and we will tell the potential of all the other things with respect to that baseline. So in electrochemistry, this is a very common baseline that we use, the standard hydrogen electrode. So if I want to calculate the electrode potential or the standard reduction potential of lithium, on one side of this battery I will have the lithium, on the other side I will have the standard hydrogen electrode. So I can change this lithium, potassium, beryllium, so whatever. So once I do this, what will be the standard hydrogen, the SRP of this thing, of the standard itself? So imagine you have this battery on which on one side you have the cathode, the other side you have the anode, right? So on one side you always have the standard hydrogen electrode, And then you're testing all these different metals. You get any type of metal or any type of non-metal that you can, and then you're measuring what is the voltage. Okay, you're keeping this hydrogen electrode fixed. And then you can have lithium, and so all the metals will get the negatives, most of the metals. There will be some metals like copper and stuff like that who will get a positive, right? Zinc will be here, copper will be here, lithium, potassium, magnesium, sodium, all will be negative. The non-metals like perchlorate, chloride, sulfate, nitrate, all these will be negative. But just imagine you get this standard hydrogen electrode on this side and also the hydrogen on this side. So what will you get? The potential. So what will be the potential of this with respect to itself? 0. Right? So that's why the potential of this will be 0, and everything else is measured corresponding to that standard value. Okay. Now, in here, let's not go into electrochemistry, but I hope that you understand that anything that will have a negative value on the standard reduction potential will be electron donors, and anything that will have a positive value will be electron acceptors, right? And it makes sense because all these metals, they want to become positive, and that's why they're dumping electrons. And lithium is one of the very reactive metals. It is dumping its electron very fast, so it becomes a very good electron donor. Make sense? And these are all negative on the right hand side of the periodic table, all these non-metals. They want to just eat electrons, so they are good electron acceptors. And that's why they have their standard reduction potential, or the potential to eat electrons, is high. That's why they have positive. Make sense? So standard reduction potential, potential to be reduced. Just remember that. Okay. Now, when we talk about life or the energy, we will also talk about things. So anything that you can eat, they will be electron donors. And then you will need an electron acceptor to get those electrons to here. Because essentially, what is energy? In biological terms, energy has a very vague definition, but what is energy? ATP. Or production of ATP is called the energy, right? So ADP to ATP, so what did we study? So ADP plus the inorganic phosphate produces ATP, and this is the energy unit in life, right? So, and this you saw in the last class that there was a process called the electron, what? Transport chain. Remember? So this was, if this is your membrane, all these different gatekeepers were here. All these gatekeepers were here, and they were producing these H pluses. And then there was this thing that was using that high potential of the protons and then driving that ATP machine, the ATP synthase. This was the ATP synthase, right? So it is all about this electron transport. Everything is about electron transport. Energy is, everything is about electrons. Anything that can give you energy is actually giving you nothing but electrons. So you need electron donors. You can only eat electron donors. So if anything, you cannot eat an electron acceptor, right? You need electron acceptors, but you cannot eat it because electron acceptors are just sucking away that energy from you, right? Because electron acceptor is what? Energy acceptor. You can think of that. Because energy has become equivalent to what? Electrons right now. Anything that gives you electrons is going to give you energy. Think of it as that way. So you need electron donors. glucose is an electron donor, C6H12O6. So you can eat glucose, it's an electron donor, and you can see that this thing is reduced in here, the carbon is reduced. So someone has taken that carbon dioxide and converted it into glucose. Photosynthesis is one of the ways, right, in which you take the carbon dioxide. So here, in here, what is the oxidation state of carbon? +4. What is the oxidation state of carbon here? What is oxygen? Typically gives you a -2. So this is -12. This is +12. So you can imagine what is the oxidation state of carbon in here, the overall oxidation state. -12 + 12, what do you get? 0. So the average oxidation state is 0, but you went from +4 to 0. So what happened to carbon? Carbon was oxidized or reduced? It was reduced. In photosynthesis, carbon was reduced. Now, because carbon was reduced, what do you think? Carbon gained electrons or lost electrons? Gained electrons, right? Because remember, what is oxidation? Is gain, and reduction is loss of electrons. I said the opposite. Oxidation is loss of electron, reduction is gain. So carbon gained the electrons. Now carbon, since it has gained electrons, now it can give you electrons. So now this carbon which has gained electrons can serve as a food. So this is food because it is a source of electrons. There will be something who will accept the electron. That's why you need electron acceptors. Now this electron acceptor could be what? Could be oxygen, could be any other thing. You just need an electron acceptor, because what does this electron acceptance do? It just converts those, it creates this proton motive force, because electrons and H+, these are connected, right? This passing of the electrons, this flow of electrons helps us to produce ATP, and that is energy. So if you want to take electrons from the electron donor and pass it to the electron acceptor, that is what you need for the flow of electrons. You ate glucose, but you also need an electron acceptor. That electron acceptor could be O2. That electron acceptor could be anything that can accept an electron. Can sulfate accept an electron? Yes, it can. Because what is sulfate a good electron acceptor? Yes. Because this is already, so if you see the sulfate reduction potential, you will see it has a positive reduction potential. So anything that has a positive reduction potential, they will be good electron acceptors. So if you see, I don't have the sulfate in here, but the CO2 glucose process, so the CO2 fixation, if you see in here, the E0 is minus 0.5 volt. Okay, so this process is reduction. The other is the O2 H2O. This is, so O2 H2O is positive 0.81 volt. So what will happen? The CO2 to glucose reduction is this. Now the glucose can dump electrons to whom? To the oxygen. What will happen to the oxygen when you dump electrons to oxygen? Oxygen will get reduced or oxidized. When you dump electrons on oxygen, it will get reduced. To what? To water in this case. And it has a positive 0.81. Okay? So in this case, glucose will be converted to oxygen, H2O, CO2 will be released. This is a big process. And energy will be released, right? Now, anything that has a positive E0 will be able to accept your electrons, yes or no? Anything that has a positive What you need is an electron acceptor, correct? To dump these electrons. Anything that can be an electron acceptor can help you out. That's it. We are only dependent on oxygen, but there could be other organisms that don't need oxygen. They might take nitrate. What they will do, they will take the nitrate and convert it to N2O, nitrous oxide, or NO2 minus or NH4 plus. They will just reduce, they will just take that nitrate and oxidize it. You can take that sulfate. What will happen to the sulfate when you dump electrons to it? Sulfate will get oxidized or reduced when you dump electrons. So taking electrons from glucose, dumping it into something. The glucose is getting oxidized to carbon dioxide. Something must be getting reduced, right? So what will be the reduction have for the sulfate? Sulfide. Right? So what could happen here is, it's a redox process, right? You have glucose and you want to convert it to something. You need energy, right? This is the electron donor, right? Correct? You need an electron acceptor. What can be the electron acceptors? O2 could be one electron acceptor. So glucose could react with O2. Let me write the electron acceptor on this side, because if there is an electron donor, you need an electron acceptor, and then this will get oxidized to what? Glucose will get oxidized to what? CO2. And this will get reduced to what? H2O. So this glucose is getting oxidized and water is getting reduced, and oxygen is getting reduced to water, right? If you use this to burn this is called aerobic respiration. This process is called aerobic respiration. Respiration is, you get food, you digest, you break down that food to get energy. That is respiration. That's it. That's what respiration. So so when you're inhaling, which is the gas that your body is using? O2. That O2 is going to your cells, that is participating in a complicated reaction that is converting the glucose into CO2, and some energy is getting released in the process. And what do you exhale out? CO2 and water. And is this an exothermic process or an endothermic process? What does it is warm, right? But then how come energy, so now can you understand like the exothermic, so like heat is getting produced, that energy is getting released, right? But if there is more of that heat coming out, less of that is being utilized somewhere. So like, we'll get to that. So your thing is to get that glucose and oxidize it to CO2. Our only electron acceptor is O2. Us, eukaryotes. We can only use the O2. But Just imagine, are there other electron acceptors available? Yes. What could be the other electron acceptors? You can have nitrate. That nitrate will go to a reduced something, N2O, for example. Will you call this aerobic respiration, or we have to change the name? Aerobic means O2. What will you name this? Anaerobic. Why? Because you are using a different electron acceptor. That's it. That's what. Someone might use NO3. Or what else can you use? Sulfate. So, can you also use iron 3? Yes, because iron 3 can accept electrons. Correct? When you get NO2 on this side, sulfate will be producing what? Sulfide. Iron 3 will be producing what? Iron 2. Can you have perchlorate? Yes. What will perchlorate produce? Chloride, chloride. These are all examples of anaerobic respiration. We cannot do this, but there will be some microorganisms that will be able to do this. Why this is important? Because oxygen was not always present in the terrestrial atmosphere or in the oceans. We did not have a lot of oxygen in the atmosphere. It only happened after the great oxidation event, right? So before that, life was present. But do you think that life was doing aerobic respiration or anaerobic respiration? Anaerobic, because there was no oxygen. Now, there are many microorganisms, bacteria, archaea, that can actually do these things. Okay? I will not go into like a lot of detail into who can do this, because these are just names, and you can read that in your in the chapter 6.7. So the section is anaerobic respiration. But just for completeness sake, this process, the NO3 minus to N2O or NO, this is called denitrification. So you have this NO3 minus and you are producing this N2O gas. This is called denitrification. There will be microorganisms who can do this. NO can also be produced. Sometimes you can also produce NO2 minus. You can also produce ammonia. So series of, and all these things are just products of nitrate reduction. That's what this is. Any planet that, so there is, and specifically this is very hard to produce N2O by anaerobic process, abiotic processes. It's very hard to produce N2O by abiotic processes. So if a planet, if you have a planet in which you can see copious amounts of N2O, that could serve as a biosignature. Okay. You probably have heard these terms. So bacteria is called Pseudomonas, Bacillus, and Staphylococcus are capable of doing these kind of nitrate reductions. Okay. Also, we saw that iron 3 to iron 2. Now this iron 3 is not present in the solution form most of the time. This could be hematite or any of these iron 3 bearing minerals. That could be a source for these kinds of iron reducing bacteria. Okay, so one of Some of the common organisms are geobacter is one of these organisms.